So I'm going to be discussing our work on measuring absorption coefficient of doped fibers using the site spontaneous emission. And the primary driver for this work is my now Dr. Mustafa Peysuhan, who defended his PhD a couple of weeks ago, and his dissertation was recommended with honor. And the original research was funded by a $7.5 million DoD Muri Award, which Professor Sheikh Bahai in the physics department is the PI, and I'm the co-PI on this grant. And also the prototype development is funded very recently from UNM Rainforest Innovation Gap funding. So let me give you a brief background on fiber lasers. So you can see fiber lasers here. I'm showing you a few applications. One of them is in automotive industries for welding. As you can see, you get very high power laser light coming out, and it allows you to do welding and machining and so on and so forth. Nowadays, there are new applications for fiber lasers in precision surgery using 2-micron fibers and so on and so forth. And of course, a particular interest in the Albuquerque area because of the presence of Air Force Research Laboratory is directed energies and defense applications for fiber lasers. So let me just give you a brief 101 introduction to fiber lasers. So as you can see, fiber lasers are lasers that are made based on optical fibers. And optical fibers are really thin, long pieces of glass. They're more like a thread. The thickness of an optical fiber typically is the thickness of human hair. The way they are made is a piece of glass, as you can see in here, is formed as what they call a preform. And the piece of glass is doped with all kinds of materials that scientists are interested. And then they take it to a draw tower, essentially heat it up and stretch it into a fine thread. And that thread that is very human hair thickness is a piece of glass, really, a glass rod, but extremely thin, and you can bend it like human hair. Not too much, of course, it would break. At the end of the day, it's glass, but it's very flexible. Now here is the optical structure on the right-hand side that scientists are interested in making for fiber lasers. Essentially, edge to edge, the thickness of this thing is it's just a piece of glass rod, but the thickness of human hair. It can be meters to kilometers long. The core of this, which is the tenth of the thickness of human hair, is the active area where you generate the laser light. And typically, this piece of glass, silica glass, is doped with an element called ytterbium. And all these flames that you see in here are doing something. Is in addition to depositing glass, they are depositing some ytterbium atoms inside the core of the fiber. And this ytterbium atoms play the role, the active role of making a laser possible. Now, on the left-hand side in the picture, I show you what you do. And when you shoot laser light, when you shoot light into these fibers, or you get the fiber to laze, to make a laser out of it, it glows, it fluoresces. And we are going to be using this glowing and this fluorescing information. And of course, this is viewed under, it's infrared, viewed under with IR glasses on an IR camera. This fluorescent we are going to be using in order to characterize this optical fiber. So what is the problem? So an optical fiber laser, here again, I'm showing you a sketch of the rod. Here to here is the thickness of human hair. The way an optical fiber laser is done is a kind of a laser that most of the lasers that you're used to seeing are, you plug it to a battery or to the wall and it generates light. So essentially it converts somehow electric current into laser light. fiber lasers are a completely different species. They convert uninteresting low brightness light, like a light bulb or something like that. These are diode lasers, but they are uninteresting and to a large extent for the purposes we are interested. Low brightness light into very, very high brightness light. So optical fiber laser is essentially a converter of a very low brightness light into an extremely high brightness light. So essentially, like if you will, a 100-watt light bulb that is so uninteresting, you turn it into a 100-watt laser. That can be a very serious machine in order to do stuff with. You can use it to machine things. It's a 100-watt laser is very dangerous. Even a 1-watt laser is dangerous, but a 100-watt light bulb that is low intensity is not. That's what the fiber laser does. So what you do is on one side of this fiber, you shoot a low brightness pump light, and it propagates through this laser, and some of it gets absorbed by these ytterbium atoms inside the core, and some of it makes it out. In this process, you generate high brightness laser light. In general, you are interested to create a condition so that this low brightness light gets absorbed in the core as quickly as possible. You want to characterize how quickly it gets absorbed. This characterization, there are different techniques to find out how to characterize how much light is absorbed per centimeter, or how quickly it gets absorbed. The standard technique that is done, that let me see if I can get this thing, bring it to the presentation mode. 1 second. All right. So the standard way is to do a cutback method. Essentially, you start from one side of the fiber, and you start cutting the fiber little by little, and measuring how much light comes out. And essentially, by how much light comes out, gradually you essentially map and find out how much light is absorbed along the fiber. And this technique is a very standard technique, is the gold standard, the cutback method, and will tell you exactly what is the pump absorption inside this fiber laser. Now, the problem is that the cutback method is destructive. Some of these fibers are very, very expensive, to the tune of maybe $1,000 to $10,000 per meter. That's not the only problem. Some of these fibers are one of a kind, meaning it would just be made once and you don't want to be destroying it. You don't have spare fibers to make these measurements. Another problem with the cutback method is you're always destroying the fiber that you're measuring. So you're always measuring another piece of fiber. You measure another piece of fiber, a different one from the one that you're going to be implementing in your device. On top of that, the cutback method involves removing the fiber from the stage, cutting it and realigning it. This is very, very tedious, and it's very hard to repeat the conditions again. So it involves mechanical tools and related uncertainties. So here is the innovation that we have come up with. And excuse the math, but really the innovation is 50% math. So I have to go through it. I hope you don't hate me much. I'll try to make this as easy as possible. So you pump laser light into an optical fiber. What happens is you catch the fiber at 2 points, point A and point B. You remember the fiber fluoresced. So you try to capture the fluorescent light from point A and point B and from the side. This is really the technique. The separation between these 2 points is some distance delta Z. We know from the absorption inside the Beer-Lambert law, inside the an optical fiber, that the power exponentially decreases. That means it gets absorbed and the power reaches from point A to point B in an exponential form. So the ratio of power B over power A is exponential e to the minus. This is the absorption coefficient that we are looking for times the distance. The distance is very easily measurable. Another point of information that we have is the amount of light that we collect in here, which is proportional to the fluorescence that comes out, is proportional to the power that of the pump that is at this point. So is the case for this point. The power, the emitted power or the collected power is proportional to how much power you have in here, and the emitted power in here is how much power you have in here. Is proportional. All you do is you divide these two, take the log, and you end up with a funny function of the log of P, the power you collect in here divided by in here, some funny constant minus the absorption coefficient times the separation. Now, the good news is that all you need to do is at this point and at this point, you need 2 power meters to measure the power and construct the ratio. You know the distance, you're looking for this thing, and this is a funny constant that apparently doesn't play a role in what we are interested in. Now, the shape of this absorption coefficient is determined by the emission fluorescence or emitted the fluorescence. You can measure it with a spectrometer. It's already tabulated in some references, either way you can use. All you need is how big is the actual coefficient to make this equal as opposed to the proportion. And that gives you the absolute value of the absorption coefficient. Now, all you do is you measure the ratio of these 2 powers. You try to vary the wavelength of the pump slightly. You need to have it slightly tunable or multiple wavelengths. And using this information, you can collect and determine the absorption coefficient. Now, this is a very interesting method because it does not involve any mechanical movement, no cutting. You're not destroying the fiber. All you're doing is probing the fiber from the side. And in fact, for a large class of fibers, once you get the spectrum from using a spectrometer, you don't even need a spectrometer. All you need to use is 2 cheap power meters. The only expensive element is the multiple lasers or a tunable laser. So this is our data, the dots, and this is sort of the theoretical. This is the fluorescence data, measured data, not the theory. And using this technique, we have measured the absorption coefficient for a particular fiber to be this number. This is the vendor spec, and we did a very careful cutback method ourselves, and we believe that our method is superior, and it actually, the vendor method, we did multiple checks, and they did the cutback method. We did it more carefully, and we think our method has lower error bars and is more robust. And besides, it did not destroy a $1,000 piece of fiber that we had. So the results have been published in an applied optics journal paper. The lead author is Mustafa Peysukan, now Dr. Mustafa Peysukan. And we have also a patent that was awarded this 2020. And UNM Rainforest Innovations, thank you, instrumental in getting this through, as always. So this is the sort of the setup of our experiment. We have an optical spectrum analyzer to collect the spectrum. We have these 2 fibers that collect the fluorescence from the side. There are some other things involved in there, for example, a long pass filter, and then we have a power meter in here and a power meter. The signal is kind of weak, so we need a lock-in amplifier to connect to the power meters. A lock-in amplifier allows you to play tricks in order to, using a chopper, it allows you to detect extremely weak levels of signal. So right now, what we are trying to do is to try to take the whole thing using the award from STC to fit it inside a box and come up with all other techniques instead of using a $7,000, $8,000 lock-in amplifier, maybe program an FPGA or something, or do a circuitry in order to replace it with something that costs less than $100 on this front. And the only expensive element would be the laser that it would require. So at the end of the day, the target for our tool will be optical fiber manufacturing, fiber laser manufacturing, and fiber laser research laboratories, that they can measure the properties of their fiber without destroying the fiber. The goal is to come up with a standalone unit costing less than $5,000. So all those tools that you saw would be fit inside the box. Project started in January 2021. The target goal is pending COVID situation, end of 2021. Hopefully, we should be able to make sufficient progress. And with that, I thank you for your attention. I'd be happy to answer any questions you have.
We'll wait 1 second, see if anyone has post any questions here. So I just have one quick question. So you said your goal is to kind of develop a standalone unit by the end of the year. Aside from the gap fund, what do you believe is necessary to actually achieve this first prototype of a unit?
Students working hard enough. If the labs don't get shut down, we should be able to do that. So I don't think there is anything that stands between us and getting this tool developed. Software would be a tricky part in commercializing this thing. So we haven't put a whole lot of thought into the software part because it depends on the elements that we are developing right now, especially the FPGA. But once that gets sorted out, then we should be able to. If not by the end of the year, this may drag on a bit longer, maybe another 3 months or 6 months. But we should be able to, with the funds provided by STC, get this going. UNM Rainforest Innovation. Sorry, I'm still going by the old names.
The last question from Edwin Namoto is, what is the projected market size for this?
It is hard to say for us. We know that the biggest optics tool maker, Thor Labs, told us that they'd be interested in licensing the technology. They didn't give us any numbers, but Thor Labs, their interest was pending that this really becomes a closed box. And we also put enough effort in order to make the software and the GUI and the toolbox really user-friendly. So, but really at the end of the day, it would be research laboratories to a large extent, and maybe a souped up version can go to laser manufacturers. If this becomes a standalone unit, there would be real interest. There are people who's gonna buy. I can't predict the actual market value for this number-wise.